has started on your PC, you can type something in the chat box for the attendance. And then you will be excused from you. I mean, I will take the attendance from here rather than from Edpuzzle for you guys who are here. So for the other people, they will be, the attendance will be taken on the Edpuzzle. Okay, so I don't know about your side, but on my side, it just gave me the notice that the recording finally got started. So some of you typed before it notified me that the recording has started. I don't know whether the earlier typing went in or not. So you might want to type again just in case. All right. Okay. So this week we are starting on sorting, and this is the first sorting lecture. There's going to be a second sorting lecture because sorting, there's a lot of different algorithms. So we'll go through the first set of algorithms today, and then next week we will go through the second set of algorithms. Okay. So we will look at many different sorting algorithms and see which data structure is most appropriate for each of the different algorithms. And after we go through all of them, then you'll be able to state 5 different sorting algorithms and sort data by hand using any of the studied algorithms and code in C++ at least 2 of these algorithms. And given a data set, choose the most appropriate algorithm to select a suitable data structure. Okay, we have seen earlier that binary search is faster than sequential search, which means, like for example, on my friend Anthony's Apple II, it would take 8 seconds versus 4 minutes for searching through all those data, but it requires that the data be ordered, okay? And therefore, actually, there are many algorithms developed for ordering. Now, you might be wondering why we are calling ordering sorting. And in computer science, we always say sorting when we mean ordering. But in English, sorting actually means putting things of the same category together, while like sorting all the white socks in the top drawer and the black pants in the middle drawer and red socks in the bottom drawer. But whereas ordering means putting things in a particular order, right? Like A to Z. But for computer algorithms, we use the word sorting to mean ordering. And the reason for this is that there was an early computer application which puts the punch cards in order. You remember that computer programs used to be, and data used to be stored on these punch cards. So computer sorts cards into bins based on their range. And then like for the first, like they have a certain number of bins in the sorting machine, and they may put 1 through 16 in bin 1, and then 17 through 32 in bin 2, and then the bin 3, you have 33 to 48. Then the next round, they'll sort the cards in each bin into smaller ranges, and so on until all of them are in the right order. So this is why in computer science, we ended up using the word sorting to mean ordering. That particular algorithm, we talked that this method is called bucket sort or bin sort because you sort things into different bins. So you might wonder, where is this algorithm used today? You still find it in places like post offices for letters. It'll sort it according to the area that it's going. Like all like if, for example, in Selangor, maybe it'll sort by all the different districts in Selangor, and then all the letters that go somewhere else, they'll put in a different bin, which will go to the main office, and then they'll sort that each district. Then you sort by the neighborhood, and then each neighborhood will go to a particular postal delivery person who will then deliver those letters. Okay, there are actually many choices for algorithms and data structures to use for ordering, and each has a different area of application. And so which algorithm you should use actually depends on the data. For example, how many individual records are there? How big are each of those individual records? Do we change the data very often? Is the data very random, or is it already mostly ordered? And also how we plan to use the data in the future. And so here we have an overview of the various sorting algorithms that we are planning to look at. Well, bucket sort we mentioned earlier just now, the physical sorting of things with using these different buckets or bins. Then there's selection sort, which usually use array of records or linked list. Insertion sort, which usually use array of records or linked list. Bubble sort uses array of records or linked list. Merge sort uses linked list and files. Natural merge uses linked list and files. And heap sort uses array of records, and quick sort array of records, and introspective sort array of records. So the bucket sort and bubble sort we actually are just going to talk about, but we don't actually implement in C++. So this module's code, this first section, is a utility code that we will use to set up the data that we use to demonstrate all sorts of different sorting algorithms and its data structures. And what it does is it just prompts the user to enter a string to sort and then allow the user to choose the sorting method. And it also has a routine to convert arrays to linked lists, because some of these sorts we want to do using linked lists. So here is the main code. This is your standard headers, and then we have this linked list definition. Since we're sorting characters, so the data in the linked list is just a character. Of course, if you are sorting something else, you just change this data to the something else and it will sort it accordingly. And then we have all these different sorting algorithms: selection sort, insertion sort, merge sort, natural merge sort, heap sort, quick sort. We got quick sort is actually a family of sorting algorithms. So there's more than one quick sort. So we're going to show two of them here. So these prototypes, we pass a pointer to the first element, which is where to start, and then the number of elements to sort. And we have this init node, which you're very familiar with from the linked list. And we have this string to list. String to list is to take the string that the user inputs and turn it into a linked list. Then this is because some of the sorts use linked list. And then print list is just to print the whole list. And then there's swap, which is just swapping two characters. So in the main, we have a string. This string is for the user to input. And then we have a pointer to the head of the linked list when you need a linked list, and the user's choice. So first we ask the user to type in something to sort. Okay, so we type in a string to sort, and then just get the length of the string. And then we ask the user which type of sort you want to use. And based on the sort, it will do the type of sort. So this is the switch to choose which sort to use depending on which sort the user chose to use. So running the program is something like this, where it will ask you for the string to sort, and then the user types in the string that they want to sort, and then the computer asks the user, choose which kind of sorting you want. You choose one, and you'll use that algorithm to sort the thing that was typed in. And we have this swap utility, which is essentially to swap the first character with the second character. That's because in a lot of swaps, in a lot of sorts, we do need to swap the data around. And then there's the string to list utility, which takes a string and creates a linked list node, first with the head node, and then we loop through the string and put the next letter into the linked list, and finally return the linked list. And so this is the list to array. This is actually a list to string. Sorry, I forgot to change this, because in C++, in C it was array. Okay, so list to string. Okay, list to string is we take the linked list and turn it into a string. Okay, so by using the next characters, add it to the string until we finish the whole string. the whole linked list. Oops, this also should be turned into a string, not n string.
N string.
Okay. So then init LL node is the same old init LL node that you're familiar with from linked lists. Okay, the first sort we're going to look at is bubble sort. And we will introduce what is bubble sort. And after that, you can use bubble sort to sort numbers on paper and understand why actually it's not a practical sort. Okay, let's look at this animation first. Okay, in bubble sort, it basically goes through and swaps any neighboring data that is not in the right order. And so the smaller elements will tend to bubble to the front while the larger elements will settle to the back. So you see here, first M and I, right? I, it should be before M, so it swaps that. Now it goes to the next spot. E and X. E should be before X, so it swaps that. Then the next spot, these two need to be swapped again. And here again, D and U will need, U and X will need to be swapped. And then P and X will need to be swapped. So you see the X has sunk all the way to the bottom, whereas all the lighter ones have gone further to the front. Then it has to go to the next again and try again, again, and then go to the front again and bubble that, and bubble that, and finally it's done. So bubble sort, everything just bubbles up or sinks down. If it's heavy, it sinks down. If it's light, it bubbles up. So this is illustration of what we saw in the animation just now. And each time it just flips to two neighboring items. So you end up with 9 swaps for this small array. And for this, then we probably want to use an array of records. And if it's a small number of things, and then you could use linked list if the individual record is small, because then when you're copying, it doesn't matter. You just kept copying a small amount of data. Linked list you could use if the individual record is large, like each item has maybe 1 GB of data. Then if you use a linked list, you don't have to copy 1 GB, just copy the pointer only. And why is I mentioned that this algorithm is quite useless. And why is it useless? It's essentially you have to do n squared number of okay, it appears I lost my connection briefly, so I shall repeat what I said on this. Right, I was already on this page when I lost my connection, right? You guys who are there? Is it correct? Yes. So I'll just start on this page. See, it is an n squared sort, but the absolute time actually is worse than selection sort and insertion sort, which we're going to discuss next. Because you definitely have to go through that many times. You cannot stop halfway that you're done. So it has no redeeming qualities except that you could use it to animate bubbles. I've actually used it to animate bubbles before in an animation. So that's about the only time that I might use this sort, not for sorting, but for animation to make the bubbles float to the top. That's all. So that it's not really a good for sorting because it's the slowest one of all of them. Okay, let's look at another one. This one is called insertion sort. And here we will look at the algorithm for insertion sorting and look at the C++ code. And after this, you should be able to do insertion sort on paper, as well as write C++ source code for the insertion sort, and also state when you might use insertion sort, and discuss what data structures are useful for insertion sorting. Okay, so this is the algorithm. When we are sorting in real life, right? One way is we pick up the biggest one and then we put it there. Then we pick the next biggest one and we try and see, does it go here or here? So we put it before, and we just keep picking the next one, and then we say, oh, this one actually goes here, you see? So this is pick it up, put it there, then pick the next one up. Does it go before or after? So if it goes before, I put it before. Pick up the next one, it goes before or after? It goes before, then I put before. Pick up the next one, does it go before or after? It goes before. And then pick up the last one and see where it goes, and it goes after, so I put it after. Okay, so let's look at it with these letters. We pick the first one, put the M there, because it's the first one. Then we pick the I. Does it go before the M or after the M? So you see it goes before the M. So we have to insert it before the M. That means you have to copy M up a bit. And then we want to put the X. Where does it go? It should go at the end, so we don't have to copy. We just put it at the end. Then we take the E. Where does it go? Well, it actually goes in front. So actually have to put it in front and copy all this to the next one. D, where does it go? It goes in front again. So I have to copy all these to the next one and put it there. And then U goes over here. So you only have to copy X. You don't have to copy the earlier ones. And P goes there. So we have to copy these last two. Okay, so this is what insertion sort does. It's called insertion sort because we pick up each item and then insert it into the proper location. So let's look at the animation. So here we have sorting by inserting into things in order. So the first one is M, as we saw before. We put the M there. Then we take the I, and we have to move the M and put the I there. Then we take the X. We don't have to move anything. It just goes at the end, right? So we don't have to move anything. Then we take the E, and we have to move I at the M and X. So you have to copy one by one, right? In arrays, you have to just copy one by one. You cannot just throw it in there. And then D, again, you have to move all four of those letters. So you copy one by one. And then you can put the D there. So this animation is a bit better than the slides because it shows you actually what the computer has to do is has to move those things. Okay, then the U, we can just copy the X over and make space for the U. Then the P, we have to copy the X and the U over to make space for the P. Okay, so that is the insertion sort. Okay, so this module's code uses that same utility code we showed you at the beginning, and it does the insertion sort, and it's just doing actually I forgot to change this. Data structure is of type string. Okay. And this one, we're going to show the intermediate steps so that you can see what's going on. So we see that for each element, you start at the beginning, then you store the current element, and starting from the last element in the sorted part of the array, while the element to insert smaller than the sorted element, we move it one position. Okay, move it one position. Then we insert the element in the correct position in the originally sorted portion of the array. So what happens? Actually, wait, I think, yeah. Okay, so this print here is just so that we can see the movement. Okay, for if you are just sorting and you just want the end result, you don't have to put this print. Okay, so what it does is right? So to say insertion sort. So first thing is M. So it has to swap this M and I. Then the X, it doesn't have to swap. It just leaves it there. Then the E, You have to swap this, swap this, swap this, and then put this here, and so on. So here is a role play to show actually the variables going on in the insertion sort. Can you hear?
No.
You cannot hear. Okay, then I need to do something different. I think I need to, because you can't hear, I need to share the, I think I need to share it as a let me stop the play first. Rewind. And then I need to share this window. Share the window. Okay. Now I think you should be able to hear if I start playing it. Play. Still cannot hear. Oh dear, still cannot hear. Let's see. Even after I share that window, you still cannot hear. Oh dear. How are we going to do this then? Okay, I tell you what, I will log in with my phone. I will log in with my phone, and then I'll use my phone to play the sound, or to put that cause echo. Like cause echo. Okay, how about I use this website instead. So then I can share the tab. And that I need to go back to my lecture notes and find that file. It's R92. R92. And I copied that into the tab. I better share the tab before I start playing it. The tab, I share the tab for Ruffle Web Demo. Okay, then I drag the R92 in there.
Basic sorting techniques, insertion sort. First, we pass a string of characters into the array A. Then, the number of characters into the integer n. Then, we declare a character holder, char, and the integers j and k. Next, we start the for loop with j equals to 0, increments up to n. We pick up m and store it in char. We start the inner for loop with k equals to j, decrements till it reaches 0. As we decrement, if we find that the preceding character is lesser or equal to char, we break out of the for loop. Otherwise, we copy the value of the preceding character into the current position. This is the way we pick up the character and look for a place to insert it. Since k is 0, the inner for loop is terminated. In essence, there's only m to insert. Then we copy the value of char into the current position. We continue to print out the integer held in j and the current value of a. Next, we increment j. We pick up I and store it in char. Now we consider where to insert I with respect to m. We search for the place by invoking the inner for loop with k set to j, decrements to 0. Since the preceding character m is neither smaller nor equal to car, we copy m into the current position. Then we decrement k. K is now 0, hence the inner loop terminates. We copy the value of car into the current position. In this way, we have successfully inserted the character I into the right position with respect to m. We continue to print out the integer held in j and the current value of a. Next, we increment j. We pick up x and store it in car. Looking at im, we try to find a place to insert x. We start the loop with k set to j, decrements to 0. Since the preceding character m is smaller than x, we call break. We copy x into the current position. Then we print out the value of j and a. Next, we increment j. We pick up e and store it in car. Likewise, we try to locate a place to insert e prior to imx. K is set to j and decrements to 0. As we proceed, we find that all the characters are not smaller than e. Hence, we insert e at the front. Again, we print out the value of j and a. Next, we increment j. We pick up the character d and store it in car. Again, we inspect the characters e, I, and x and look for a place to insert it. Since all of them are not smaller than d, we insert d at the front. Then we print out the value of j and a. We perform the same operations until j increments up to n. Once j reaches n, the sorting process is complete.
Okay, so that was the insertion sort role play. So let's look at it. How does this code work? See, we have the j directed at the first unsorted element, okay, starting 0 here. And we store the current value of this element into this temporary variable that we will be referring to. And then we shift all the elements to make a space as long as the current element is less than, as long as the thing we're looking at now is less than that element that we stored earlier. Say this is, it means because if it's smaller, right, we need to shift it. Right? So we have to shift it to make space. So we shift it to make space. We shift it to make space. So this is what's going on here. And then once we've finished already, that means that there is enough space and we can put that element there. Okay. So how long does this take? We first approximate by the double loops there, which means that it's going to be O of n squared, just like bubble sort. But for a sorted array, it breaks out the inner loop. So actually it's just O of n. So because for sorted data, this is always true. So that's why it can run faster. So in this selection sort, if your array is partially sorted, it actually runs faster. So where will we use these algorithms? If your array is already mostly sorted, and for example, if you had a previously sorted name list of 1,000 names, and you just had to add 10 new names, then this is a good algorithm to use. And what data structures is appropriate? If the size of individual record is small, then you might as well use array of records because it's easy. But if the size of individual record is big, then you might want to use linked list so that you don't have to copy so much data at one go. Okay, now let me make this maybe as a poll so that you can all oops, oh no, I press escape in the wrong window. Poll, start a poll, oops. And then, so what is the second step? Okay, remember the first step. Okay, let's make a poll. Okay, you guys can see the poll, so you can make your guess. Remember, so the first step is we look at P, right? And we see, do we need to swap P and O, right? Well, no, first step is we look at P and see, do we need to swap P and P? So of course it doesn't swap lah. So then when you look at the second step, you're looking at P and O. What happens? Okay, I have only 2 of you have voted. What about the rest? Make a guess lah, wrong, never mind lah. At least we can discuss, right? Come on, the rest of you. Three of you have voted. How about the rest? Okay, there are 5 of you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 10 of there are 11 of you, but 5 of you only have voted, so less than half. Come on, just if you're wrong, don't worry if you're wrong. This is not an exam, okay? This is so that you can think and have an idea of how the algorithm actually goes. 6 have voted. What about the other 5 people? Okay, 7 people have voted. Okay, I think we'll end the poll now. Okay, so all the 7 people who voted chose this one. And in fact, it is because remember the first one we look at P. Of course, you don't swap P with P, but then look at PO, you see that O is less than P, so it will swap that one. Okay. Then the next step, then you'll look at P and I and then decide to swap that. That's for the third step lah. All right. So that is insertion sort. Now let's go on to the next sort, which is selection sort. Okay, selection sort. We're going to first introduce the algorithm and look at the C++ source code. And after this, you should be able to use selection sort to sort numbers on paper and write C++ source code for selection sort and think about and be able to tell when you use the selection sort and what kind of data structure. Okay, so in real life, like if you're doing selection sort, we might look at a bunch of blocks and find the smallest block and put it in the right place. Then find the next smallest block and put it in the right place, and so on, right? So here's what it does. So we choose the smallest one, move that to the right place, take the next smallest one, put next to the right place, and the next one, and move it, and the next bigger one, move it, and then finally the last one, we move it. So this is how we do a selection sort. Okay, so in the example here, we look for the smallest one. The smallest one is D. So we swap it with the M, which is the right place is in the front, right? So we swap the D with the M, which is the right place. Okay, that's what we do first. Then the next smaller one is the E. So we swap that with the next place because this one already sorted, right? D already sorted. So we exclude it from consideration. We only look at what's left and then we swap it and we get there. And then the I is the next smallest one. So we swap it. And then the next smallest one is the M, so we swap that. Then the next smallest one is the P, so we swap that. And the next smallest one is the U, so we swap that. So then we're done. So here we look at the selection sort. So the animation, again, we are looking for the smallest one and moving it to the front. Right? So here, the smallest one is D, so we move it to the front, which means we have to move the one from the front somewhere else, which is swapping it. Then the next smallest one, E, and swap it. Next smallest one, I, and swap it. And next smallest one, M, and swap it. Next smallest one, P, and swap it. And then after that, you don't have to swap the U and X because it's already in the right place. So the modules code uses the same utility code we saw in the beginning, and it uses the algorithm of selection sort. And again, we are doing strings. Okay, so here we are looking at the smallest unsorted element. We keep track of that, remember, because the sorted ones, we don't have to look at it again. And then we start at the beginning of the array. For each position in the array, of the string, each person of the position of string, find the smallest element in the sorted position of the string. Okay, of course, array, it works exactly the same way. In fact, a string is underneath, it's really an array. Okay, so we look for this. We start at the beginning, look for the smallest one. Okay, look for the smallest one here in the part that isn't already sorted, and we put it in car. And then when we find it, we swap it. Okay, and then we just print the intermediate output. So 5 swaps are required, which means 15 copies. So here you look for the smallest one, and then you swap it. Okay, so here the E and the I swap, and then here the next one, and so on. So at this point, it's the correct order already, but it still has to go through the rest of the loop. Oh, selections. Okay, so here again, we have to use the ruffle web, be able to build it. And this was R92. Okay, let me get the R92, and we need to share the present tab, ruffle web, and then R92 select. Okay.
Basic sorting techniques, selection sort. First, we pass a string of characters into the array A, then the number of characters into the integer n. Then we declare the integers min, j, and k, and a character holder char. Next, we start the for loop with j equals to 0, increments up to n. We set min equals to j, and we start an inner for loop with k initialized to j, incrementing up to n. While incrementing, we compare the current character in k with the character in min. If the character in k is smaller, then we assign min to k. In this case, I is smaller than m, hence we assign min to k. Next, x is bigger than I, so we don't do anything. Then E is smaller than I, so we pass min to k. D is smaller than E, so we pass min to k. Once k reaches n, the inner loop terminates. We set char to copy the character held by min. Then we copy the character in j into the position of min. Then the character in char is copied into the position of j. In this way, we have swapped the character in min and the character in j. We continue to print out the integer held in j and the current value of a. Next, we increment j. Note that we have selected the smallest letter from the string and put it in front, which means we don't have to consider that letter after this. That's why j starts from this position. Mean is then set to j. K is initialized to j and increments up to n. While k is incrementing, we compare the character in k and the character in mean. If the character k is smaller, we assign mean to k. The loop comes to an end when k reaches n. Then we swap the characters between mean and j. We continue to print out the integer held in j and the current value of a. Next, we increment j. So C, D, and E are put in front, which means the sorting operation later will not involve them. Mean is then set to j. The k loop starts from j and increments up to n. Whenever the k character is smaller than the mean character, mean is set to k. The loop ends when it reaches n. Then we swap the characters in mean and j. Then we print out the value of j and a. Similarly, we repeat the whole process until j reaches n. By the time j finishes incrementing up to n, the string is finally sorted.
Okay. So let's examine the code. We have first the j is the first unsorted element, right? So we put mean is j. We're now going to find this and store the index of the smallest element after j. So we look through here, look for it, find it, and then we sort the smallest element with the index of j here. Then j becomes the next element, and we continue that again. So how long does this take? Again, we have double loops, so it's going to be in the order of n squared, even for a sorted array. So this is a serious problem because you'd be wasting your time sorting through a sorted array. So when will you use this algorithm is only if there's a small data set, data is already in a random order, and sorting needs only to be done once. And what kind of data structure? Array of records is probably best if the size of an individual record is small, and linked list could also be used if the size of an individual record is large. Okay, so let's have another poll. Create a poll. Oops, keep pressing escape in the wrong window. Create a poll. Click here and then press escape. Okay. So what is the first step for selection sort? Okay. You have to find the smallest one, right? Select the smallest one and put it in front. This should be quite simple, right? Yeah, you have a question? Someone raise a hand. Also an accidental raising of hand because I think the hand has gone again. Okay, it's an accident. So far, we've only had 4 votes. There are 9 of you. Okay, 5 votes. Okay, 6 votes. The other 3, are you sleeping? There are 9 of you, but I only see 6 votes. Okay, everybody chose the ones that start with I because we said select the smallest one, right? So we are looking at the smallest one, which is I, which is why everybody chose either B or C. Okay, but when you choose I, you put it in the front part, which means you're swapping it with the P. Okay, the I swap with the P. So you're going to I, O, P, and T. It's this one. So the majority chose this one, which is wrong. You're just looking at the first letter. It's not. Why would it swap N there? We haven't swapped N yet, right? It's only this one because we swap I and the P. I said the first step. So I swap I and the P. So the P goes there. The I goes in front, the P goes there. The rest haven't changed places. All right? So in this case, the majority was wrong. But there were some people who got it right because they realized that it's just swapping those 2 letters and nothing else. Okay? Okay, so I actually only prepared this much for today. So it's a short lesson because I didn't want to, I wasn't sure how long it'll take and everything, but we'll continue next time with the other sorts. All right. So thanks for coming, and the other people will have to watch it on the Edpuzzle. I'll stop the recording now.